This is one of the most important videos of this semester where we introduce the gradient, section 13.6, and look at the directional derivatives. Alright, so let's start in 2D. So a function of two input f, x, y. And what does it mean to be differentiable for such a function? So we saw that in the last section, the last video, the partial derivative. So what happens when I vary x keeping y constant, and what happens when I vary y keeping x constant. Okay? And we saw some example where actually, well, the derivative might depend on the directions. And we want to look at functions that are differentiable, meaning that whatever direction, no matter how I approach the given point where I want the derivative, it's well defined. Okay, so here's the precise definition. So we say a function is differentiable if for any curve xt, yt, okay, that when t tends to 0, I get to that point. Okay, so I approach that point. So that means, okay, so I have different curves. However I approach that point, and now there's an infinite number of ways to approach that point. I can take different kind of curves to approach it. When I take the limit t tends to 0 of the function at a point xt, yt, close to it, okay, minus the function at that point, and I divide by the distance that I am away from x0, y0 at the time t, well, this limit exists. Okay, then we say that the function is differentiable. All right. Okay, so most of the time we will actually deal with function. We saw some singular cases, but let's assume from now on that we deal with functions that are differentiable, so I can approach the point and look at how the function vary in the different directions. All right. So let's assume, for now on, that the function we're dealing with is differentiable. So then we can define what we call the directional derivatives. Okay. So the directional derivative du in the direction u. Okay. So the idea right is, okay, I have this point x0, y0. So I want to approach it from different direction. Okay, and this direction, we know we can quantify, or we can define a direction using a unit vector. All right. Okay. Now, let's relate that to what we know. So if I look at the partial derivative of f with respect to x, so remember what this means? It's the change in f when I move by 1 unit in x. Okay? Why? Because, well, it's the usual ratio, right, that you should think of the derivative as the limit of the variation in f divided by the variation in x in that case. And what we do for the partial derivative with respect to x is fixing this y0. Okay? So if you think about that, that's the rate of change of f by units of x, because I divide by delta x. Okay? So this gives you the change in f when I move by 1 unit in x, because I divide by the length of x. Okay? So it's the rate of change, the x direction. Now we want to do exactly the same thing in the u direction. So that was if you want the x direction. So now what about I take the direction u? Okay? So it's the same meaning. That means that duf will be the change of f when we move one unit in the direction of u. Okay, so I'm sitting here at this input, and I want to know if I take one step in that direction, okay, what's my rate of change? Okay, so very important, u is the unit vector. It's a unit vector, okay? Now here's the definition, and I'll show you what it makes sense. So the directional derivative of f in the direction u at the point x0, y0 is the partial derivative of x of f with respect to x times ux, okay, where ux is the x coordinate of u, plus the del yf times the y coordinate for ui. So what does that mean? I want to change up f, so I go ux unit in the x direction, and I multiply by the rate of change in the x direction. So that gives me how much I change due to the movement in x. And now to go really to the u direction, I still have to do step y. So I have to add how much change of f is due to the moving uy steps in the y direction. Okay, so this makes sense. So the change of f in the u directions is the rate of change in x times how much unit I move in x, and same thing for the y direction. Okay, now here's the one conceptual step. I realize that this is as the form of a dot product, right? Because I multiply the x coordinate, I multiply the y coordinate. So I should see this as a vector. And that vector is the gradient, one of the most important objects in this class. So wait, this is a dot product, okay? It's a dot product between the vector u, the unit vector, the direction, times the gradient. This is what we call the gradient of f at a given point, okay? So the gradient of f, so this inverse triangle is the gradient of f at the point x0, y0 is del xf, that's the x coordinate, so partial derivative with respect to x at that point, that's the y coordinate of the gradient, and the y coordinate is the partial derivative in y at that point, okay? So x coordinate, y coordinate, and I can also write it using the unit vector if I want in the respective direction, okay? So the gradient is a vector, okay? All right, so let's do an example here. So find the directional derivative of the function x squared sine of y at the point 1 pi over 2. Okay? In the direction of v equals 3i minus 4j. Okay? So how do I do this? Well, what's the gradient at the arbitrary point xy? Well, first I have to take the derivative with respect to x, so that gives me 2x sine y. For the x coordinate and for the y coordinate, I take the partial derivative with respect to y, so I get ix squared cosine y. And so if I evaluate it at the point 1 pi over 2, this vector gives me sine of pi over 2 is 1, so I get 2 here, and cosine of pi over 2 is 0, so I get 2, 0. Okay, so now what's the direction? Is 3 minus 4. Now this is not a unit vector, so I need to normalize. So what's the norm of v? Well, it's 9 plus 16, square root of that, which is 5. So the unit vector is 3/5 minus 4/5. So if I want the derivative in the direction of v, at the point 1 pi over 2, this is equal to 2, 0 times 3/5 minus 4/5, which is equal to 6/5. Okay? So that's how you do the directional derivative. All right. Now here are three general properties of the gradient, and I'm going to show them in class. You can think about it. They're pretty simple to show. First of all, if the gradient is the zero vector, okay? So what I mean that is the zero vector, then obviously the directional derivative will be zero in any direction, right? And so that gives me a point where in any direction, if you want, I stay flat. So that's the equivalent of a stationary point, okay? So it's the same thing as in 1D. When the derivative is zero, then that means that the tangent line is horizontal, right? And this is where I look for local maximum and local minimum, possibly inflection point, okay? So that's going to be the equivalent of that in higher dimension when we look at extrema. So when the gradient is a vector 0. Now, if I look at the direction of maximal increase, it's actually given by the direction of the gradient. Now I normalize because I just want the direction. Okay, so if I'm sitting on my surface and I want to know I want to go in the direction when my function varies the most, goes up the most, I go in the direction of the gradient. If I want a minimal increase, I'm going to go in the minus direction of the gradient. So we'll show that in class. Okay, and the other interesting properties is that when I look at the gradient at a given point, x0, y0, okay, so that sits on the level line which is given at the value by the value of the function at that point. So if I trace all the points whose value is the same as the one at x0, y0, I get a level line, okay? And if I look at the tangent to that level line at the point x0, y0, well, this is perpendicular to the gradient. So the gradient always points perpendicular to the level lines, okay? So it's exactly if you think about that, when you climb a mountain, right? So, and you look at a topographic map, if you want to go in the direction of maximal increase, you will go perpendicular to those level lines. Now you might say, well, there's two directions being perpendicular. That's true. So one is of maximal increase, one is of minimal increase. So one thing is going up the mountain, one thing is going down the mountain the quickest way possible. All right. Little word about higher dimension, the same thing applies, okay? So just to be simpler, we focus on 2 dimensions, but I can define the gradient for a function from Rn to R, where I have n input and 1 output. And then the gradient is, again, a vector. It's an n-dimensional vector, okay, that whose coordinates are simply the partial derivative of that function in every coordinate. And if I want the derivative of that function going in a particular direction in the n-dimensional space, well, I pick a direction that is a unit vector in Rn, and I just do the dot product with the gradient of f. Okay, and the dot product is the sum of the product of every coordinate of the 2 vector. Okay, and the same property holds, that is, well, if the gradient is 0, I have a stationary point, it's flat. If I want the direction of maximal increase and minimal increase given by the direction of the gradient, and the gradient will be always perpendicular to the level lines or level surfaces, or anyway, the geometric shape that's given by the points that have the same value. All right? Okay, so this is about the gradient, one of the most important objects in this class, one of the most important video as well, and we're going to see that object till the end of the class. Thank you for listening.